Welcome to the new episode of Chatting with ChatGPT, where we explore the fascinating world of natural language processing, artificial intelligence, and all things related to ChatGPT. In this episode, we'll take a deep dive into anatomy of ChatGPT and explore the inner workings of the GPT architecture. From the generative model to pre-training and fine-tuning, we'll examine the building blocks that makes up the state-of-the-art language model. We'll also explore the key components of the transformer architecture, including self-attention, multi-head attention, feed-forward networks, layer normalization, and positional encoding. Just a heads up, this discussion will be more technical, and let's get started. Hey ChatGPT, what are you made of?
Hi, as an AI language model, I am not made of physical materials like humans or machines. Rather, I exist as a complex software program that runs on powerful computer servers. My brain is made up of advanced algorithms and models that have been trained on vast amounts of data to enable me to understand and generate natural language.
Got it. Are you cloned from GPT?
I am not a clone of GPT, but rather a similar type of language model. GPT, generative pre-trained transformer, is a type of machine learning model that has been trained on large amounts of text data to understand and generate natural language. Similarly, I am a large language model that has been pre-trained on vast amounts of text data and fine-tuned to perform a range of language tasks, such as answering questions and generating text. While I share similarities with GPT, I am a distinct and unique AI language model developed by OpenAI.
I see. Let's talk about generative. What do you mean by generative?
In the context of language models like GPT and me, generative refers to our ability to generate new text based on the input we receive. We are able to produce coherent and contextually appropriate text that resembles human language, even though we don't actually understand the text in the same way that humans do. The generative aspect of these models comes from their architecture, which involves a series of neural networks that are trained on large amounts of text data. These networks allow the model to learn patterns in language and generate new text by predicting the most likely sequence of words given the context and any provided prompt. This ability to generate new text is what makes these models so useful for a variety of language-related tasks, such as chatbots, language translation, and text summarization.
Okay, let's move on to P in the GPT, that is pre-trained. What do you mean by pre-trained?
In the context of language models like GPT and me, pre-training refers to the process of training the model on a large amount of text data before it is fine-tuned for a specific task. During the pre-training process, the language model is exposed to vast amounts of text data, allowing it to learn patterns and relationships within the language. The pre-training process typically involves a task called unsupervised learning, which means that the model learns from the raw text data without any explicit supervision or labeling of the data. The model uses a technique called self-supervised learning to predict missing words or next words in the text, based on the context of the surrounding words. This process helps the model to develop a general understanding of the structure and patterns of human language. Once the pre-training process is complete, the language model can be fine-tuned for a specific task, such as language translation or text classification. During fine-tuning, the model is trained on a smaller, labeled dataset that is specific to the task at hand. Fine-tuning allows the model to adapt its pre-existing knowledge to the specific requirements of the task, resulting in a more accurate and useful language model.
What is T in the GPT?
In the GPT model, T stands for transformer. The transformer is a neural network architecture that is a critical component of the GPT model. It is responsible for modeling long-range dependencies in sequential data, such as natural language text. The transformer is composed of multiple layers of self-attention mechanisms and feed-forward neural networks, which enable it to capture complex patterns and relationships within text data. This architecture has been highly influential in natural language processing and has been used in a wide range of applications, from language translation to text generation.
Perfect. Thanks. Let's talk about the transformer in the GPT in more detail. Do you know there is a technical paper called Attention is All You Need that was published in 2017?
Yes, I am familiar with the technical paper, Attention is All You Need, that was published in 2017. The paper introduced the transformer architecture, which is a type of neural network architecture that has become a fundamental building block for many state-of-the-art language models, including GPT. The transformer architecture uses a self-attention mechanism to allow each position in the input sequence to attend to all other positions in the sequence, without requiring explicit alignment information between the positions. This allows the network to capture long-range dependencies and relationships between different parts of the input sequence, which is particularly important for language models. The self-attention mechanism allows the network to calculate a weighted sum of the representations of all other positions in the sequence, with the weights determined by a learned attention mechanism. This attention mechanism allows the network to give more weight to the parts of the sequence that are most relevant for predicting the next token in the sequence. The transformer architecture has several advantages over previous neural network architectures for language modeling, including the ability to process input sequences in parallel, and the ability to scale to longer input sequences without requiring excessive memory usage. These advantages have made the transformer architecture a popular choice for many state-of-the-art language models, including GPT.
Let's deep dive into the architecture of the transformer. What are the key elements and the components of the transformer architecture?
Sure, I can give you a high-level overview of the key elements and components of the transformer architecture. Encoder and decoder. The transformer architecture is composed of an encoder and a decoder. The encoder processes the input sequence and produces a sequence of hidden states, while the decoder takes the encoder output and generates the final output sequence. Self-attention mechanism. The transformer uses a self-attention mechanism that allows each position in the input sequence to attend to all other positions in the sequence. This mechanism allows the network to capture long-range dependencies and relationships between different parts of the input sequence. Multi-head attention. The self-attention mechanism is performed multiple times in parallel, with different learned projection matrices used to generate different representations of the input. This is known as multi-head attention, and it allows the network to capture different types of information and relationships between the input sequence elements. Feed-forward network. The transformer also includes a feed-forward network that is applied to each position in the sequence independently. This network consists of two linear transformations with a ReLU activation function in between, and it helps to capture complex nonlinear relationships between the input sequence elements. Layer normalization. To improve the stability of the training process, the transformer includes layer normalization, which normalizes the inputs to each sublayer of the network. Positional encoding. Since the transformer architecture does not use recurrent connections or convolutions, it includes a positional encoding mechanism that allows the network to incorporate information about the order of the input sequence elements. These are the key elements and components of the transformer architecture, which has proven to be a highly effective building block for many state-of-the-art natural language processing models.
Regarding encoder and decoder, you said the encoder processes the input sequence and produces a sequence of hidden states, while the decoder takes the encoder output and generates the final output sequence. It is very interesting mechanism here. Can you be a little more specific and detailed about this?
The encoder takes the input sequence of tokens and applies a series of multi-head self-attention mechanisms and feed-forward neural networks to encode the input sequence into a set of context vectors, which capture the semantic meaning of each token in the sequence. The decoder then takes the encoded context vectors and uses them to generate a target sequence, one token at a time. The decoder also includes a multi-head attention mechanism that allows it to attend to the relevant parts of the encoded input sequence at each step of the decoding process. The encoder and decoder work in tandem to process input sequences and generate output sequences, such as in the case of machine translation. The encoder takes in the source language sentence and produces a set of context vectors, which are then used by the decoder to generate the corresponding target language sentence.
That is great explanation. Thank you. Let's turn our attention into attention. That is self-attention, I mean. Can you please elaborate? What do you mean by self-attention and how it functioning within the transformer architecture?
The self-attention mechanism allows the network to calculate a weighted sum of the representations of all other positions in the sequence, with the weights determined by a learned attention mechanism. This means that for each position in the input sequence, the network can attend to all other positions in the sequence to determine how important each of those positions is for predicting the next token in the sequence. To compute self-attention, the input sequence is transformed into three matrices: the query matrix, the key matrix, and the value matrix. The query, key, and value matrices are linear transformations of the input sequence, with learnable weights. For each position in the input sequence, the self-attention mechanism computes a weighted sum of the values, with the weights determined by the similarity between the position's query vector and all key vectors. The similarity between the query vector and the key vectors is calculated using the dot product, and then the resulting attention weights are normalized using the softmax function. Once the attention weights have been computed, the network can use them to obtain a weighted sum of the values, with the resulting vector representing the context for the position in question. This context vector is then passed through a feed-forward network to produce the final output for that position. By performing self-attention at each position in the input sequence, the transformer is able to capture long-range dependencies and relationships between different parts of the input sequence, without requiring explicit alignment information between the positions. This makes the network highly effective for natural language processing tasks, which often involve capturing complex relationships between different parts of a sentence or document.
You said multi-head attention, and it allows the network to capture different type of information and relationship between the input sequence elements. I think I need a little more explanation than that.
Sure, I'd be happy to explain multi-head attention in more detail. In the transformer architecture, multi-head attention is used to allow the network to capture different types of information and relationships between the input sequence elements. This is accomplished by performing self-attention multiple times in parallel, with different learned projection matrices used to generate different representations of the input. Specifically, multi-head attention involves splitting the query, key, and value matrices into multiple heads or submatrices, each of which is transformed independently using its own set of learned projection matrices. The output of each submatrix is then concatenated and transformed using another learned projection matrix to produce the final output of the multi-head attention layer. The number of attention heads is a hyperparameter of the model and is typically set to a value between 8 and 16. By using multiple attention heads, the transformer is able to capture multiple relationships and patterns in the input sequence, rather than relying on a single attention mechanism. Multi-head attention has been shown to be highly effective for a variety of natural language processing tasks, including machine translation, text generation, and question answering. The ability to capture multiple types of relationships between the input sequence elements is a key factor in the transformer's success, and has made it one of the most widely used architectures for natural language processing.
So the output of each submatrix is then concatenated and transformed using another learned projection matrix to produce the final output of the multi-head attention layer. That is amazing mechanism. Let's talk about feed-forward network. How this function works, how critical this component for the transformer.
The feed-forward network is a key component of the transformer architecture, and it is used to process the output of the self-attention mechanism in each layer of the network. The feed-forward network consists of two linear transformations followed by a nonlinear activation function, typically the rectified linear unit, ReLU. The first linear transformation projects the input to a higher dimensional space, while the second linear transformation maps the output of the ReLU activation function back to the original dimensionality. The ReLU activation function is used to introduce nonlinearity into the model, which is critical for capturing complex patterns and relationships in the input. The feed-forward network is applied independently to each position in the input sequence, and its output is then added to the output of the self-attention mechanism using residual connections. These residual connections allow the network to propagate gradients more effectively during training, which can help to prevent the vanishing gradient problem that can occur in deep neural networks. While the self-attention mechanism is critical for allowing the transformer to capture long-range dependencies and relationships in the input, the feed-forward network plays an important role in processing this information and extracting features that are useful for downstream tasks. The nonlinear activation function in the feed-forward network allows the network to learn complex representations of the input, which can help to improve the accuracy of the model on a wide range of natural language processing tasks.
Layer normalization. Can you explain that with an example?
Layer normalization is a technique that is used in the transformer architecture to normalize the output of the self-attention and feed-forward network layers. The goal of layer normalization is to reduce the internal covariate shift, which is a phenomenon that occurs when the distribution of the input to each layer changes during training, making it difficult for the network to learn stable and effective representations. In the transformer architecture, layer normalization is applied to the output of each self-attention and feed-forward network layer. Specifically, layer normalization involves subtracting the mean and dividing by the standard deviation of the activations in each layer, using learned parameters for each layer. For example, let's say we have a transformer model with 6 layers, and we want to apply layer normalization to the output of the third layer. We would first calculate the mean and standard deviation of the activations in the third layer, and then subtract the mean and divide by the standard deviation to obtain a normalized output. The resulting output would then be passed to the next layer in the network. Layer normalization has been shown to be highly effective for a wide range of natural language processing tasks, including machine translation, text generation, and question answering. By reducing the internal covariate shift, layer normalization can help to improve the stability and performance of the network, leading to better results on a variety of benchmarks and applications.
In the transformer architecture, layer normalization is applied to the output of each self-attention and feed-forward network layer. I say, that makes sense. The last one of transformer architecture, positional encoding. Please elaborate in detail, ChatGPT.
In the transformer architecture, positional encoding is a technique that is used to incorporate information about the position of each element in the input sequence into the representation that is used by the network. The key challenge in using self-attention to process sequences is that self-attention is permutation invariant, meaning that it treats each element in the sequence as interchangeable with every other element. This can make it difficult for the network to capture the sequential relationships between elements in the input, which are often critical for natural language processing tasks. To address this challenge, the transformer uses positional encoding to introduce positional information into the input representation. Positional encoding involves adding a fixed vector to each element in the input sequence, where the vector is chosen based on the position of the element in the sequence. By using different frequencies for each dimension of the input embedding, the network is able to learn representations that capture both the content and the position of each element in the input. The positional encoding is added to the input embeddings for each element in the sequence before they are processed by the self-attention and feed-forward network layers. This allows the network to capture both the content and position information of each element in the input, which can improve its ability to model complex relationships and dependencies between elements in natural language processing tasks.
Thank you. I want to talk about two important techniques of GPT, which makes GPT better. One is prompt engineering, aka prompt design, also fine tuning. Let's talk about a prompt design.
Prompt engineering is the process of designing high-quality prompts for a language model to improve its performance on specific tasks. It involves creating input templates and guidelines that guide the model towards the desired output, as well as providing examples of the types of inputs and outputs that the model should be able to handle. Prompt engineering is particularly important for fine-tuning a pre-trained language model on a specific task, as it allows the model to be trained more efficiently and effectively. By providing high-quality prompts, the model can learn to generalize to new inputs more accurately and efficiently, resulting in better performance on the target task. In summary, prompt engineering is a critical step in the fine-tuning process that enables the creation of more powerful and accurate language models. It involves carefully designing and curating input data and examples to guide the model towards the desired outputs.
Okay, how to become expert in prompt engineering?
Becoming an expert in generating effective prompts for language models like GPT and me requires practice and a deep understanding of the language and context that you are working with. Here are a few tips that may help you improve your prompt writing skills. Be clear and specific. Provide clear and specific prompts that clearly communicate what you are looking for. Avoid ambiguity and be as precise as possible in your language. Use examples. Providing examples of the kind of response you are looking for can help guide the language model and increase the likelihood of generating a useful response. Understand the model's capabilities and limitations. Be aware of the language model's strengths and weaknesses, and tailor your prompts accordingly. For example, some models may struggle with certain types of language or may perform better with specific types of prompts. Practice and iterate. Generating effective prompts is a skill that can be improved through practice and iteration. Experiment with different prompt styles and formats to see what works best. Overall, becoming an expert in generating effective prompts requires a combination of knowledge, experience, and experimentation. With practice, you can learn to write prompts that help language models like me generate more accurate and useful response.
What are the few key skills that you think it can be helpful for to become a skilled prompt designer?
To design effective prompts, you should have strong language skills, including a deep understanding of grammar, syntax, and semantics. This will help you communicate your intent clearly and ensure that the language model can understand what you're asking for. You should have some knowledge of the domain or subject matter you are working with. This can help you craft prompts that are specific and relevant to the context, which can improve the accuracy of the language model's responses. Designing effective prompts also requires technical skills, including knowledge of how language models work, familiarity with the tools used to interact with them, and an understanding of how to interpret and analyze the model's responses. Finally, designing effective prompts often requires a certain degree of creativity, as you may need to find innovative ways to ask questions or frame prompts in order to get the information you need. With practice and experience, you can develop these skills and become more effective at generating prompts that help language models like me generate accurate and useful responses.
That was very useful. Appreciate that. Tell me about what is fine tuning. Can you explain within an example?
In the context of language models like GPT and me, fine-tuning refers to the process of training the pre-trained model on a smaller, labeled dataset that is specific to a particular task. The goal of fine-tuning is to adapt the pre-trained language model to the requirements of the specific task and improve its accuracy and performance. For example, let's say you wanted to use a pre-trained language model to generate product descriptions for an e-commerce website. To do this, you would first fine-tune the pre-trained model on a dataset of product descriptions, providing labels that indicate the category of each product, example, clothing, electronics, books, etc. The fine-tuning process involves updating the weights of the pre-trained language model to optimize its performance for the specific task of generating product descriptions. During fine-tuning, the model learns to associate the language used in the product descriptions with the specific categories of products. This enables the model to generate more accurate and relevant product descriptions when presented with a new product category. Fine-tuning is a powerful technique for adapting pre-trained language models to specific tasks and domains, and it can be used for a wide range of applications, including language translation, text classification, and sentiment analysis. By fine-tuning a pre-trained language model, you can achieve high levels of accuracy and efficiency for specific language-related tasks.
How can one become an expert in fine-tuning ChatGPT?
Becoming an expert in fine-tuning language models like GPT requires a combination of technical and domain-specific knowledge. Fine-tuning language models requires a solid foundation in programming and software development. You should be familiar with programming languages such as Python and have experience working with libraries and frameworks commonly used in natural language processing, such as TensorFlow or PyTorch. To fine-tune a language model effectively, you should have a solid understanding of natural language processing, NLP, and the different techniques and algorithms used in the field. This includes knowledge of text preprocessing, feature extraction, and machine learning algorithms. To fine-tune a language model, you should be familiar with the pre-trained models available and understand their strengths and weaknesses. This can help you select the best model for your task and optimize its performance during fine-tuning. Finally, to fine-tune a language model for a specific task or domain, you should have some knowledge of the relevant domain. This can include understanding the vocabulary, syntax, and common patterns of the language used in that domain, as well as any specific challenges or nuances related to the domain.
ChatGPT, we covered a lot in this episode. We gone through anatomy of GPT and you have patiently answered many of our questions. It is complex, but you tried your best to explaining how the inner functioning of ChatGPT works. Thank you for your time. I really appreciate that.
I'm glad I was explaining me about who I'm and how I designed to function. Thanks for inviting me. See you later.
See you later, ChatGPT. In this episode of Anatomy of ChatGPT, we explore the inner workings of GPT model and its architecture. We started by discussing the meaning behind the acronym GPT, which stands for Generative Pre-trained Transformer. We then delve into the individual components of GPT architecture, starting with generative aspect. We discuss the concept of generative model and how GPT leverages its pre-training to generate text in a way that is both coherent and contextually relevant. Then we deep dived into transformer architecture, including its key components such as self-attention, multi-head attention, and feed-forward networks. We explore how these components work together to enable GPT to process and understand the natural language text. We then moved to discuss the pre-trained aspect of GPT, including how pre-training works and its advantages over the traditional machine learning models. We also explored the concept of fine tuning, which is the process of adapting a pre training model to a specific task, and how prompt engineering can be used to improve the performance of a fine tuning model. Thank you for joining this episode, Anatomy of ChatGPT. We're looking forward to see you in future episodes. Until then, keep chatting.
Thanks for tuning into Chatting with ChatGPT. We hope you enjoyed this episode and found it informative. If you have any questions or topic suggestions for future episodes, please reach out to us on our social media channels. Remember to follow, like, and subscribe for more conversations with ChatGPT. Until next time, keep chatting.